All right, so this is the plum pudding model. This is model number 2 of the ones that we're studying in this unit about atoms. So the first question here, which you are not going to be able to see in this video very well, but is, do you prefer which is your favorite thing to snack on? Plum pudding, watermelon, or a blueberry muffin? So the reason why I ask is because this model looks a lot like one of those. You have a like fluffy, positive fluff here, and then you have negative electrons like the blueberries or the watermelon seeds or the plums in the plum pudding. So we are going to be exploring the history of understanding about atoms in this investigation. So if you'll remember, since 400 BC, this is kind of the model that we had about the atom. It was just a solid sphere with uniform properties, and that's what people thought that they would look like or be like since the beginning of when people thought about this. But then, J.J. Thomson performed an experiment that changed the model of the atom forever. So what this was is a cathode ray machine, which was it's plugged to a power source, and there's a negative charged plate here and a positively charged plate there. So this electricity is coming from the cathode over to the anode, and it creates a stream of glowing particles across this vacuum tube here. This happens because there is very little air in the tube here, and that's what makes it so that you can actually see the stream of particles going across. And what J.J. Thomson noticed is that when he put some electric fields nearby or some magnets nearby, the stream would bend, and he wanted to know what was going on there. So there is a video just about this that I'm going to let you watch. It's also linked in the Google Classroom, J.J. Thomson's cathode ray experiment. So let's fill in the blanks here. Oh goodness, we can't even see it all. So the other thing that is interesting about a cathode ray machine and finding out what these particles are, we found out that these particles are actually electrons, which are a subatomic particle that have a negative charge. And they have an atomic mass that is tiny. It's smaller than even the tiniest atom by a lot. And that is why the negative charge plus the fact that they are so small is why bringing a charged plate near here would make that stream bend. But just to find out some more, he did some different experiments where he shot smaller atoms across here to see like if they would have an impact or if they would be bent by these electric fields. And what he found was that no, they're not. They're not bent by electric fields the same electric fields that bend the cathode rays. They require much, much stronger charges of electric field or stronger magnets by like thousands of times stronger to bend that ray. So what that tells us is that these mystery cathode ray particles are very, very small. Like I said, like thousands of times smaller than the smallest atom. If you would like to practice with that simulation, which I would recommend before the test, you should go into the Concord STEM resource, Activity Investigation 4, Activity 2, page 3, and you can play with with the cathode ray machine and see how that impacts those rays. So when we talk about electrons as subatomic particles, what that means is that they are even smaller than atoms. They are very small. So we now know that this is what an atom really looks like. Now, of course, we can't actually see atoms even with a microscope. They require like a very specialized thing that senses the bumps in the electromagnetic field. I mean, they're really super duper small. But the idea here is that we have tiny negatively charged electrons orbiting around a dense positively charged core. So that changed the model completely, right? Before we had the simple model with a solid uniform sphere, and now we think that maybe there are some charges inside of this atom. Maybe the bulk of the atom is positively charged, and then there's these negatively charged electrons in there, like blueberries in a blueberry muffin, or seeds in a watermelon, or plums in a plum pudding. So how does a simple model of the atom compare to a plum pudding model of the atom? The plum pudding model has charges, and specifically positive and negative charges. And again, those negative charged electrons are like the blueberries in the blueberry muffin, or the seeds in the watermelon, or the plums in the plum pudding. So this is what he came up with. And the reason why, the way that I help to remember that these are the negative blueberries and whatever is because when I was a kid, I loved blueberry muffins, but I really didn't like blueberries. So I was really confused about why they would want to have something so negative like a blueberry inside of this delicious, fluffy, sweet blueberry muffin. So that's how I remember the negative blueberries in the blueberry muffin. So the advantage of the plum pudding model is that it explains that electricity is moving electrons. That was really important to realize. I mean, the fact that electricity is actually a bunch of subatomic particles on the move is like a crazy thought, and it's pretty awesome. And they also now understand that positive and negative charges are both inside of the atom, and also that negative charges can be separated from the atom. But it doesn't solve all of our questions. The disadvantage is that it assumes that atoms are a solid, positively charged mass, like a blueberry muffin, and we will soon find out that they are not a solid mass at all. They're mostly empty space. It also assumes that electrons are spit out of atoms like seeds out of a watermelon, which is not how electrons move. So let's see. So are you convinced that this is the final model that we're going to sit with for the rest of eternity? You should not be convinced, because we're about to crumple this model up and find out something different based on the experiment of Ernest Rutherford. But for now, you can go to the Google form, The Cloud of Electrons, and fill that out.